Hello learner, greetings of the day. Let's discuss about three-dimensional rotation. We have already discussed about three-dimensional translation and the corresponding matrices required to perform translation. So now let's discuss about the rotation. As we already know, what are the factors that is required for performing rotation? If it is a 2D rotation, what are the factors? And now what are the factors required to perform rotation about 3 dimension? So the first and important factor to perform rotation is the rotation angle theta. And the second one is the axis required to perform rotation. So now when I say the axis required to perform rotation, this time since it is a 3D rotation, I can make use of x-axis, I can make use of y-axis, and I can also make use of z-axis along which the object could be rotated. So these are the three axes along which the object could be rotated. The third factor required to perform rotation is a vector. Vector, when I say a vector, it's nothing but the direction along which we rotate the object. So when I say a direction there, direction could be anti-clockwise direction or it can be clockwise direction. So in both the direction I can rotate the object. So it is anti-clockwise direction or clockwise direction. So that is decided by the vector. So as you all know now, the components required to perform rotation is, one is the angle of rotation. So again when I say the angle of rotation, the angle can be negative angle or positive angle. If the angle of rotation is negative, then the direction of rotation changes from anti-clockwise to clockwise direction. Or if the angle that you pass, the angle of rotation that you pass is a parameter, if it is a positive one, then by default always the direction of rotation becomes anti-clockwise. So you have two types of rotation, two angles, negative or positive, depending upon the direction of rotation. So these are the factors that it is required to perform rotation. And you can just see here in the figure, the viewer is over here and the viewer is actually a human eye. Now you can see the object is rotating. See, the person or the viewer is in front of the object there. So he is now performing the rotation about z-axis. So since it is an anti-clockwise direction, we must have passed positive angle theta, rotation angle theta, and then the vector about which we are rotating here decides the direction there. And now the angle of rotation or the axis of rotation here is along z-axis. Now if I perform, you can see now the viewer is in front of x-axis. So now the object will be rotated along x-axis, and now the viewer is looking upward from the top direction, and you can now see that the object is rotated along y-axis. So these are the three directions of rotation, three axes of rotation: x-axis, y-axis and z-axis respectively. Now we can just start with the three-dimensional rotation equations. So as we have already written the equations for performing two-dimensional rotation, it will be easy for us to analyze three-dimensional rotation equations. So to begin with, let's start with the z-axis rotation equations. So what are the equations required to perform z-axis rotation along z-axis? So here, as the axis is z-axis, remember I can directly write the equation as z dash, or the new coordinate that I obtained after performing the rotation along z-axis is, z values are unchanged. If I'm rotating the object along z-axis, that means z values remains unchanged or it remains constant. So immediately you can write the equation as z dash is equal to z, because z value doesn't change, right? So the new point is same as the old point, but what changes there is x and y. So how do I write the equation for x and y? So you can see here the component of x along horizontal, that is x cos theta, minus the component along y-axis, that is minus y sin theta. So this is an equation for x dash, and we have already seen how did we get this particular equation when we discussed about two-dimensional rotation. So you can just go back to the video of where I explained about two-dimensional rotation, and you can go through there how the equations are written. Similarly, y dash is equal to x sin theta plus y cos theta, and finally what remains unchanged there is the z values. And now, keeping these three equations in mind, can we just convert this into the matrix format? Yes, the LHS here I can write it in the form of a column matrix. This LHS I can write it in the form of column matrix, which is given in the homogeneous coordinate form. When I say a homogeneous coordinate, since it is a three-dimensional rotation, my order of the matrix is 4 cross 4. Okay, 4 cross 4. So now LHS, when I am writing, this represents a new point after rotation. New point after rotation. So I can write it in the form of a column matrix, which is given by x dash, y dash, z dash, and the fourth element here is 1, which indicates the reference point, that is origin about which we are rotating the object. So x dash, y dash, z dash, and 1. Now coming to the RHS part, you can see the first row indicates all x values. So the first row indicates x values. You can see the equation corresponding to this first x coordinate. So you can write it as cos theta, that is a component of x, minus sin theta, that's a component of y, and the z component in the first equation is 0. You can write it, and since the matrix is a 4 cross 4 matrix, I must have the fourth component, and the fourth component here is 0. Now you can go for the second equation. So what is the second equation saying? X sin theta. So component of x is sin theta plus y is cos theta. So the component of y is cos theta. Z value is 0, and the fourth element is also 0. Now the last equation, z dash is equal to z. So here you can see x value is not there, y value also is not there, only the z value you can see. So you can directly write it as 0, 0, and last the z component is 1, and the fourth element is anyways 0. And since it is a homogeneous coordinate system, there is a fourth row which indicates that the origin reference point there. So you can write it as 0, 0, 0, and the last element is 1, which indicates the reference point, that is origin. And now what you can do here, you can multiply this entire matrix with our original point. So I can have my original point written in the form of a column matrix. So what is that component? X-axis x component, y z coordinate, and the last element is 1, which indicates it's a origin. So now you can just say as post multiplication, like we have already. What is post multiplication? Always start from right to left. So the first point, original point, you have to now multiply with the rotation matrix, and this rotation matrix, you can see this, I can call it as a standard rotation matrix along z axis, where theta is angle of rotation. So original point is multiplied by the rotation matrix in order to get the new point, okay, new rotated point. Okay, so that is given by P dash. So you can write it as a general equation. Okay, this is about the rotation. Now you can refer the same equations and write the subsequent rotation equations, that is next to rotate the object, how to rotate the object along x-axis, then how to rotate the object along y-axis. Write the equations for that and write the corresponding matrices. Okay, so you can just see here, if suppose I want to rotate about the other two coordinate axis. So other two coordinate axis, that is given by x-axis and y-axis other than z-axis. So here you can perform something like this: first x, then y, then z, and then you can come back again you can start with x. Okay, so the transformation equations for rotations about the other two coordinate axes can be obtained with the cyclic permutation of the coordinate parameters. So cyclic permutation is in order x, y, z, and then again x. Okay, we can see now the rotation equations along x-axis and then along y-axis. So like we already wrote the equations for performing the rotation along z-axis. We kept all z values constant. And now when we speak about the rotation, or when we perform rotation along x-axis, all x values remains unchanged. Now what changes there is only the y and z-axis, z values. So how to write this equation now? You can just refer here. Earlier, you had an equation for x-axis. So that was x cos theta minus y sin theta. All that you have to do now is just shift these values. That's all. You have to shift these values now in such a way that y gets this. Okay. So what is it? X, all the component of x moves to y, whereas the component of y moves to z. Like how I already said in my previous slide, the cyclic permutation. So what is that cyclic permutation there? Earlier z values, when we rotated along z axis, all the values that you had for x, now it moved to y. Okay, and all the values that you had with y, okay, that components moved on to z. Similarly, all the components that you have in z, that will move on to x. So when is this cyclic permutation happens? That is here. See, so as I already said, earlier we had x cos theta minus y sin theta. So when you're performing rotation along x-axis, now x values remains unchanged. So this is not there. But now you have to write a new equation for y dash. But how do you write that new equation for y dash? Refer to this old equation. See here, y dash when you write, as I said, earlier it was x cos theta, now that should be shifted to y. So now it became y cos theta, you can see it became y cos theta, and then minus y sin theta was there earlier, and now you have to go with the cyclic permutation, so y values will move to z. So now it should become, instead of y, z. So minus z sin theta. So write it as minus z sin theta. So this is called cyclic permutation. So now y dash is equal to y cos theta minus z sin theta. Now you can write the equation for z. So now you have to write the equation for z. For writing the equation for z, you have to refer which equation? The y dash equation. So now z dash is equal to, see, again the cyclic permutation you have to go with. So x will be shifted to, x value will be shifted to y, and then y value will be shifted to z again. Y value will be shifted to z again. So you can write the new equation for z dash. Z dash is equal to, so y sin theta, okay, plus, instead of y cos theta, now it became z cos theta. So that is a new equation that you write for z dash, whereas x values remains unchanged. So this is actually how you write the equation for performing the rotation along x-axis. Now I guess you can write the equation for performing the rotation along y-axis. Yes, for performing the rotation along y-axis, which equations you have to refer? Now you have to refer to this previous set of equation what you had already written. So remember now, since you are rotating along y-axis, what values remains unchanged? It is the y values remains unchanged. You can write it as it is, y dash is equal to y. Now you can start with the first equation. See, earlier the first equation we had started with y dash. Now since it is a cyclic permutation, after y which comes? It is z comes. So right, you can begin with z. So z dash is equal to, so earlier the y equation was like y cos theta. Now the cyclic permutation says after y it is z. So z cos theta, write it, z cos theta minus, after z what should come? X again. So minus x sin theta. So this is the equation that you write for z. Next you refer to the next equation z dash. So after z what comes? X. So write it as it is, x dash is equal to, so after y it is z. So write z sin theta plus, after z cos theta what it comes? After z it's x again. So plus x cos theta. See, components remains unchanged. What changes there is only x, y and z values. Okay, and y dash is equal to y finally. So once you write these equations, now you can actually write your matrix also. You can write it easily, your matrix. Remember, when you write the rotation matrix for x-axis, the first row remains unchanged. So how do you write the first row? X component is 1 and rest all the other 3 values values that you have, it should be 0. So when it comes to the second row, you have to refer to this equation and write first value is 0 because no component along x. Next comes cos theta, then minus sin theta, then 0. Again the third equation, so again first component is 0, start from second y component, that is sin theta, cos theta, 0, and the fourth row is 0 0 0 1. Okay, so similarly you can write the rotation matrix for y axis. So I'll leave it as an exercise for you all. So you have to write the matrix, rotation matrix, standard rotation matrix, that is Rx theta, standard rotation matrix Rx theta. So you must write this rotation matrix. Okay, when you are writing this matrix, you can refer to the rotation matrix that we have already written for Z, and you also have to write the standard rotation matrix for Ry theta. Okay, so this also should be written. And suppose now I have to perform the rotation along clockwise direction. So when I perform the rotation along clockwise direction, it's a reverse one. So always replace theta with minus theta. So replace theta by minus theta, and whenever you replace this theta by minus theta, it becomes cos of minus theta is equal to plus cos theta, whereas sin of minus theta, it will become minus sin theta, remember. So all the matrices changes there whenever you try to perform inverse rotation. So remember, theta should be replaced by minus theta. Okay. Now let's see how we perform general three-dimensional rotation. So what is general three-dimensional rotation? You can just see the scenario. I have an object somewhere placed over here. Okay, and I have some coordinates also to represent this object coordinate system you call. Okay, so here you can see a pyramid kind of, it's a pyramid 3D shape, and here you have 4 vertices that you have represented, 4 vertices. I'm sorry, there is one more vertex there. There is one more vertex here which is hidden. So 4 vertices which forms the base, and then one vertex that forms the apex, a pyramid shape. Okay, and this is an object now which you have to rotate along x-axis. Say I want to rotate this object along x-axis. So how do I perform this rotation? Remember, all the rotation matrices that we have written so far, or we have represented, whatever we have represented so far, all those rotation matrices are written with respect to origin as the fixed point. So what is the meaning of that? The rotation is, or in the previous rotation matrices, we have referred to this origin. With reference to this origin as fixed point, we have written those matrices, right? So now here you are asked to perform rotation along x-axis about some point. Say that some point, let me take it as some center of the pyramid, somewhere over here there is one center point. About that point I have to rotate the object, and about which axis? It is about x-axis. So how do I perform rotation in that case? Okay, so in all my previous equations, my fixed point about which I am rotating was origin. So what should I do now? You can just go with the sequence, or you can just go with the procedure there. Since this is the original position of the object, you can simply translate the object in such a way that the axis of rotation will be x-axis. Why? Because I want to perform the rotation along x-axis only. So translate or shift the position in order to rotate the object along x-axis. Okay, once you have shifted here along along x-axis, what you can do now? You can now perform the rotation. So since I am performing the rotation by an angle theta now, along which axis it will rotate? It will rotate along x-axis. Why? Because object is already translated to a position such a way that the object is aligned along x-axis. Once it is aligned along x-axis, now you can do the actual rotation. So that is rotation along x-axis. After performing the rotation along x-axis, you cannot leave the object over here in this position. This rotated object, you cannot leave it in this position. So what you have to do, after this rotation, completion of rotation, you can shift the object back to its original position. So which object this time you are shifting? It is the rotated object that you're shifting back to its original position. The shifting procedure, you call it as reverse translation. So first what we had done, original object was there. Next we got this original object to, we translated it forward in such a way that the object aligns along x-axis. So once it aligns along x-axis, what you can do, now you can perform the actual rotation along x-axis. Now you can't leave the rotated object there. You have to shift back the rotated object to the original position. That can be done by performing reverse translation. So reverse translation takes the object back to its original position. So this is actually a general three-dimensional rotation. Like I already said, first one is translation, to align, then perform the actual rotation, and then translate the object back to its original position. If I am writing it in the form of an equation there, you can write it in this way. If I take a object as a simple point which I have to rotate along x-axis, okay, this is a axis, x-axis, along which I want to rotate. So this is actually the y-axis, and this is finally our z-axis. Okay, so this is our axis about which I want to rotate. Now here is a point P which I have to rotate. So what you can do, first translate the object in such a way that the object aligns along x-axis. So first and foremost transformation that you're applying is translation, and onto which you are translating, which one you are translating, the object that you're translating is a point. You can represent this point in the form of a column matrix. Now this point matrix, column matrix, should be multiplied by what? A translation matrix. So first translation you apply, and now you can rotate the object. You can rotate the object along, say, x-axis by an angle theta. So since the object is already aligned, you can now easily rotate along x-axis, and after rotating the point, you cannot leave the point in that new position. You have to shift the object back to its original position, and this time you are shifting back. So it's a reverse translation that you're applying onto the rotated point. Okay, so this rotated point will be now reversely translated to its original position. So by doing this, you get a new point, and that new point is a new rotated point. Okay, so this is how you write an equation. Okay, so this is an equation, and this term you can write it in general something like this: r of theta is equal to, in general. Okay, so you can write it as t into like rx theta into t inverse. No, this is something like, that sequence of rotation whatever you are performing. Okay, that sequence of transformations that you are applying, translation, then rotation, and then reverse translation, that you can generally write it as r of theta. Okay, so in general you can write this something like this: p dash is equal to r theta, r, which is nothing but the sequence of transformation that you have applied, multiply that with original point. Okay, so this point can be replaced by any other object now, need not be always point. Okay, so it's a post multiplication, so right to left the multiplication takes place.